A singularity.
The space-time singularity. So the universe born from a black hole exploding.
It's just like being in empty space for us. We would just be talking now when we could have been talking on the outside of the horizon, and by the time I finished the sentence, we could be on the inside of the horizon, inside the black hole.
Prominent scientists have proposed that there exists a realm inside a black hole, a mirror world where space and time swap places.
The language that we use for space-time and black holes bear a profound imprint of the language that we are developing.
But Professor Nikodem Popławski takes that idea even further. He believes that our entire universe is the one that exists inside a black hole.
Every black hole creates a new growing universe inside the event horizon.
That what we perceive as the Big Bang wasn't the beginning from nothing, but the bounce from another collapsing universe.
That matter after the bounce has to expand somewhere, so it expands into a new space.
It's a radical thought that what lies outside isn't just an empty void, but the parent universe, evolving along spatial directions while our own reality flows through time. A realm where our time is someone else's distance. And at the furthest edge of what we call the universe could lie the other side of a black hole. And that's where today's journey begins. Black holes are among the most extraordinary phenomena in the universe. They represent regions where gravity becomes so extreme and space and time themselves bend. It forms boundaries where the known laws of physics begin to collapse. In Stephen Hawking's collected scientific papers from the book Hawking on the Big Bang and Black Holes, one of his most striking insights concerns the nature of phenomenon. He stated that the early universe cannot have been completely homogeneous and isotropic, because galaxies and stars would not have formed. Here, Hawking and his collaborator Jonathan Halliwell emphasized that tiny irregularities in the early universe were essential. Without them, the perfectly smooth cosmos would never have evolved into galaxies, stars, or any large-scale structure at all. These minute fluctuations also opened the path for black holes. Unlike galaxies that radiate light and matter outward, black holes trap everything that comes too close. Once something crosses the event horizon, there is no return. And so, inside this boundary, the roles of space and time effectively reverse, and the usual rules of escape no longer apply.
The black hole is a region of space and time where the strength of gravity is so high that light has no path to get out of the object. All paths through space-time curve back in on itself. That edge, beyond which there's no return, we call the event horizon.
But how can a black hole continue spinning indefinitely while remaining stable over time? So to answer this, he defined measurable physical quantities that describe a black hole, and those are mass, the surface area of its event horizon, angular momentum, and the electric charge. From these, he and others derived a set of equations linking these quantities together, producing what are now known as the 4 laws of black hole mechanics. If you ask me, these laws in some ways extend the 4 laws of thermodynamics. The 0th law: the surface gravity of a stationary black hole is constant across its event horizon. This means that the gravitational pull at the edge of the black hole is uniform everywhere when the black hole is in a steady state. No side exerts a stronger force than another. The 1st law: any small change in a stationary black hole's mass is exactly balanced by changes in its horizon area, angular momentum, and electric charge. From here, we know that this relationship acts as a kind of cosmic ledger. Even if an object falls into a black hole and is stretched into what physicists call spaghettification, the information it carries, like its mass, spin, and charge, is not destroyed. It becomes encoded in the so-called black hole's balance sheet. The 2nd law: the total area of a black hole's event horizon never decreases over time. When two black holes with areas A1 and A2 are merging, the resulting black hole has a new area, A3, that is greater than the sum of the two initial areas. So, in other words, black hole horizons can grow, but they can never actually shrink. The third law. It is impossible by any physical process to reduce a black hole's surface gravity to zero through a finite sequence of operations. No matter how you might try to manipulate it, like by spinning it faster or adding mass, you can never reach perfect stillness. Achieving zero surface gravity would require an infinite number of perfectly tuned interactions, and, not to mention, infinite time. So, if it were possible, it would expose a naked singularity and, at the same time, violating the foundations of modern physics. If we look closely at all four of these laws, they all converge on one key concept: the event horizon. Each law speaks about it, its gravity, area, or how it changes with mass, spin, and charge. And so, the event horizon is the central stage where all black hole mechanics take place.
If you went in across this region, 3 kilometers, you went inside it, you couldn't get out. So that's called the event horizon. So you wouldn't notice if you fell through the horizon of the black hole in the Milky Way galaxy.
Interestingly, the idea of a horizon doesn't end with black holes, because, in a way, our entire universe has one too, a cosmic horizon. Can you guess which one it is? Well, if we think of a black hole's event horizon as the limit beyond which nothing can return, then our universe has a similar boundary, the limit of what we can see. And as you've probably guessed, we call it the observable universe. It's the cosmic bubble that contains everything whose light has had time to reach us since the Big Bang. And because the universe has been expanding all this time, that horizon stretches out to about 46 billion light years in every direction. Beyond this limit may lie regions of space that exist, but remained forever hidden from us, because their light has not yet had time to reach us since the Big Bang. And so, this leads to an intriguing perspective. The term event horizon describes the limit seen by an observer outside a black hole, while the observable universe represents the horizon for an observer within the cosmos itself. In both cases, the boundary of what can be known depends on the position of the observer, and this is perfectly consistent with the principle of relativity.
Time freezes and we cannot go beyond. If time on a spaceship crossing black hole freezes to zero relative to our time, that means we will never see the spaceship crossing the event horizon. So basically, from our perspective on Earth, the spaceship will cross the event horizon after infinite future.
In 2014, astrophysicist Nikodem Popławski published a paper titled "Universe in a Black Hole with Spin and Torsion." In it, he proposed a remarkable idea, that the interior of a black hole could be interpreted as a new closed universe, born through a process known as a cosmic bounce. He introduced a modified version of the Friedmann equation, the one that governs the expansion of the universe. This equation serves to explain how this whole scenario could occur, as one of the criteria for its work. But what does this really mean? Let's briefly dissect this puzzle. When you hear the term black hole, you probably imagine a tiny dot that swallows everything around it. But mathematically, the situation inside a black hole is far stranger. Within the event horizon, the coordinate we normally call space begins to behave like time, and the coordinate we call time starts behaving like space. This means that once you cross the event horizon, you can no longer stay still. Everything is compelled to move towards smaller values of r. In the same way, we are all inevitably moving forward in time in this universe. And so, from that perspective, the interior of a black hole behaves much like an entire universe that evolves over its own time dimension. Einstein's general relativity describes gravity as the curvature of space-time produced by mass and energy. but Popławski works with a slightly modified framework called the Einstein-Cartan theory. It preserves the idea of curvature, but adds an additional geometric property known as torsion, a kind of intrinsic twist in spacetime caused by the spin of matter particles. It is represented by this term in this modified Friedmann equation. For simplicity, this accounts for spin torsion repulsion, a kind of force that becomes significant at extremely high densities.
Torsion manifests itself like a gravitational repulsion, which means when the matter wants to create a singularity in a black hole, the matter reaches extremely high densities, much bigger than nuclear density, and then torsion, which is negligible.
Now, as matter inside a collapsing black hole is compressed to insane densities, Popławski suggests that the effect of spin becomes dominant. At some critical density, the spin-torsion repulsion becomes strong enough to halt the collapse, preventing the formation of a true singularity. Mathematically, when the energy density epsilon equals the spin-torsion term, the contraction stops, at which A dot reaches 0. At that point, a bounce occurs instead of a singularity, where the scale factor A would otherwise shrink to nearly 0. So what exactly is the deal with this? Well, in this description, instead of the usual singularity that we know, the interior of a black hole reaches the smallest possible size and then re-expands. You can think of this phenomenon as dropping a super bouncy ball. What matters is that the ball compresses at impact and then it rebounds and flies back up.
Big bounce means very huge deceleration. Matter collapses very quickly and then suddenly it stops and bounces back. You go from contraction to expansion, so there's a huge acceleration. So gravitational field changes in time very, very quickly according to the Hawking radiation.
And this part really blew my mind. As you've probably noticed, once the event horizon forms, nothing inside can communicate with the outside. Not even information, light, or quantum bits. That means whatever happens after the bounce, this so-called new expansion, or the created mini-universe, is completely invisible to the original universe. But from the perspective of observers inside that newly formed cosmos, it would appear exactly like living in an expanding universe. They would see galaxies moving apart, the CMB cooling down, just like everything we observe in our own universe. According to Professor Popławski, it's the truly mind-blowing fact that the interior of a black hole becomes a new closed universe. And so, what if our universe as we know it today is part of something like this? That our reality now, or the scientific term of what we call the observable universe, is nothing but a closed universe inside the massive interior of a black hole, the one that exists beyond everything we know. So, to summarize, Nikodem Popławski argues that the conventional idea of the Big Bang that we all know is actually a big bounce. The formation of a new universe with a completely separate space-time structure. And all of that happens inside a black hole.
If singularity is avoided in a black hole and the matter bounces back and starts expanding, that matter after the bounce has to expand somewhere, so it expands into a new space.
Later in this video, we'll cross that boundary, beyond the edge of our universe, into the possible realm outside the black hole that could contain everything we know. I mean, if our reality truly exists within one, it might just change how you understand existence itself. If you like this hoodie, make sure to check out our merch. We've got a ton of designs that spark fun banter at parties. See the link in the description below. Modern cosmological observations confirm that the universe's expansion is accelerating and not slowing down. Over time, that acceleration suggests that the scale factor of the cosmos is growing faster and new space is being created between existing points. It's the reason why this picture of the observable universe is not 13.8 billion light-years in radius, simply because it's been expanding faster and faster all this time. And here's a good analogy. If cosmic expansion can accelerate outward, perhaps our mental horizon can accelerate too. I mean, growing ever larger as we train our minds. For instance, repeated exposure to challenging tasks in math, logic, and abstraction can strengthen relevant circuits in the brain, which makes your brain adaptable over time. And this is the core reason why we partner up with Brilliant.org. It's a learning app designed to make understanding truly stick. Every lesson is hands-on, letting you experiment with ideas and see how concepts work in real time. Like this one, for instance. How many rotations does the blue gear make when the yellow gear completes 8 rotations? You can pause this section to think this through. Well, we know that the compound gear on in the middle completes 4 rotations when the yellow one completes 8. And then the blue gear completes 2 rotations when the compound gear on the left completes 4 rotations. So 2 is the right answer. Brilliant helps sharpen the way you think and solve problems through thousands of interactive courses in math, science, programming, data analysis, and AI. All of their content is crafted by an award-winning team of professionals from Stanford, MIT, Google, Microsoft, and many more. You can start exploring Brilliant for free, and there's also an exclusive 20% discount on the annual premium plan. Just head over to brilliant.org/beyondideas, or simply scan the QR code on screen to begin unlocking new ways of learning every day. Now, we step back and look at these ideas. If space-time can actually bounce or even repeat, then the next question is, what does the evidence actually say? Modern astronomy is no longer confined to theory. With instruments like the James Webb Space Telescope, we can now look deeper into time than ever before. And what we're finding is both surprising and unsettling. In September 14, 2015, LIGO detected a signal carrying information about a pair of distant black holes that had spiraled together and merged. It looked something like this. That signal had traveled for about 1.3 billion years across the universe before reaching Earth. It did not emit light, but instead carried gravitational waves, tiny ripples that stretch and compress space as they move. This marked the first time humanity had ever heard the universe through the warping of space-time itself. And a decade later, in January 2025, another merger event, named GW251-114, gave scientists an even deeper insight. By analyzing its gravitational wave frequencies, researchers verified Hawking's second law of black hole mechanics. As we've mentioned before, it's the fact that the total surface area of black holes can never decrease. This confirmation came from studies at Northwestern University. In the same year, James Webb also revealed something even more puzzling. You see, in a random universe, we would expect roughly equal numbers of galaxies rotating clockwise and counterclockwise. But the deep field observations suggested otherwise, that most galaxies appear to rotate in the same direction. This one really gets you thinking. If the universe was born from a truly random explosion like the Big Bang, then galactic rotation should also be random. So could it be that our universe has been rotating since the beginning? And if so, where did that spin originate? This ties back to our earlier discussion today. Professor Popławski offers one possible explanation. He says that our universe was born rotating. It's a natural consequence of being formed from within a spinning black hole in another universe. And so, to an external observer, that black hole would appear as a dark point in their sky. But to us, inside it, that point would be the entirety of our cosmos. In the end, this explanation aligns with the black hole cosmology hypothesis, which suggests that our entire universe exists inside a black hole.
The horizon of the universe has all the same properties as the event horizon of a black hole. We would be living evidence of a universe inside a black hole.
And so, once the universe came into existence, how did it evolve into what we see today? In 1985, Stephen Hawking and James Hartle described in their work on the origin of structure in the universe that before there was space, time, or even atoms, the universe was governed by quantum fluctuations. They're tiny, random jitters, like little waves of energy flickering in and out of existence. And then, as the universe rapidly expanded during the event known as cosmic inflation, those minute fluctuations were stretched across enormous scales, which would then become the seeds of everything: galaxies, stars, and the vast cosmic web we observe today.
Inflation is the idea that space-time was around before the Big Bang, and it was expanding extremely fast. And it was doubling in size.
The authors went even further, suggesting that the universe itself can be seen as one giant quantum wave. Before our specific universe came into being, there existed only the possibilities of many universes, and ours was one that became real. This transition from possibility to reality is explained through what physicists call the freeze-out moment. During inflation, space expanded so rapidly that those quantum waves could no longer change. They became frozen into place. Random fluctuations solidified into real structures and settled the blueprint for all matter and energy that followed. And so from these frozen ripples, the universe began to take form. What started as chaotic quantum energy eventually became the universe we know today.
All fields, all quantum fields, have tiny fluctuations in them. They are not isotropic either.
Quantum physics enabled this universe.
Now, we're getting into one of the most mind-bending consequences of the idea we've explored so far. We'll ask the question, what actually lies outside our observable universe, if indeed we live inside a massive black hole? So for this next part, we'll take the most extreme assumption, that our universe truly exists within the interior of a black hole, and that the cosmic horizon we see is nothing but the event horizon of that black hole, as viewed from the outside of it, which is kind of rational since we can't receive anything beyond it. At least, not until the universe keeps expanding, and the radius of the observable universe grows larger and larger over time. So what lies beyond this reality? Here's the thing. The space outside our universe would belong to the parent cosmos, the larger reality in which our black hole was formed. But the geometry there wouldn't behave the way ours does, just like inside the event horizon of any black hole in our universe. Three dramatic things happen in Einstein's equations. 1 is that the sign of the metric flips. 2, the space coordinate, or r, becomes time-like. And 3, the coordinate t becomes space-like. Inside the event horizon, every possible future leads towards smaller r. And that's why physicists say all world lines end at the singularity, because mathematically, r equals 0 acts like a future moment in time for everything that falls in. And so the same thing applies when we extrapolate this idea to the outer edge of our universe. Because the moment matter crossed the event horizon to create our universe, the roles of space and time switched. Inside our universe, time flows away from the bounce, just as it flows forward from our Big Bang. But from the outside, space behaves as time does for us. So in that outer world, the dimension we experience as time passing might be nothing more than a distance you can walk, while what we call space might be what they experience as an unstoppable forward flow. I guess that sounds a bit too complicated to describe this reality verbally, but what if we try to visualize it in a way we can actually comprehend? You know that here in our reality, we have 3 spatial dimensions and 1 temporal. The temporal flow always moves forward, whether we like it or not. Meanwhile, we can freely move within the 3 spatial dimensions forward and backward, left and right, or up and down by jumping. Now imagine flipping that scenario. This time, you could navigate along the time axis, literally moving to the past or the future. Yet, the spatial dimensions always move forward. So is there anything like that we can relate to in our daily lives? Well, it took me a while to find the right analogy, and I almost left this part out, until I had an epiphany while walking through Chenxi Airport in Singapore. You've seen it, right? The giant walkway. On it, we always move forward. So let's assume it's forbidden to go back. And realistically, most people wouldn't do it anyway. But that's a spatial totem that always moves forward, whether you like it or not. And then you might ask, what about the time options that we could navigate? Well, how about imagining each boarding gate as a freedom of choice for the time we could pick? So if you decide to enter a specific gate, you'd be transported to a different point in time, where you could move around and explore it. So in that scenario, if we had an apparatus that could grant us access to different events, which allows us to teleport to any moment in time, the possibilities would essentially be endless. You could visit your own childhood bedroom. You could attend someone else's graduation and materialize nearby, or stand next to your friend during their childhood birthday. In this case, time is very much navigable. The only thing you cannot do is go backward along the walkway. Of course, we're only scratching the surface here. There's a lot more I could explain about the mechanics behind this concept. Just drop this emoji in the comments if you'd like us to feature this idea in another video. But the staggering message is this: what lies outside our observable universe might be a realm beyond our comprehension. Because through evolution, we've been conditioned to think and perceive within the familiar boundaries of the reality we inhabit. So even the simple idea of space and time swapping feels too complex to comprehend. That explaining it requires layers of analogies. And maybe if all those analogies were stripped away, and we were faced with the raw logical structure of what truly exists beyond our universe, we simply wouldn't be able to comprehend it, let alone experience it.